More than 1 million miles from Earth, a telescope the size of a tennis court drifts in permanent shadow, its gold-coated mirror staring into regions of space that appear completely black to human eyes. It waits, sometimes for days, collecting individual photons that began their journey when the universe was less than 500 million years old. Those photons carry information that has forced astronomers to revise fundamental assumptions about cosmic history. When the James Webb Space Telescope began returning data in 2022, the numbers didn't match predictions. Galaxies appeared in eras that should have been nearly empty. Structures emerged far earlier than theoretical models allowed. And the deeper Webb looked, the more crowded the early universe became. This isn't speculation. Between August and September 2022, Webb's near-infrared camera captured images of galaxies whose light had been traveling for more than 13 billion years. Spectroscopic analysis confirmed their distances. Mass estimates, derived from luminosity measurements and stellar population models, showed objects containing hundreds of millions of solar masses already assembled within the universe's first 500 million years. According to conventional structure formation timelines, that assemblies should have required significantly more time. The contradiction isn't subtle. Published studies from multiple independent teams reported galaxy number densities in the early universe roughly twice what standard cosmological models predicted. The measurements have been repeated using different instruments and calibration methods. The discrepancy persists. If you value content built entirely on verified observations and measured data, rather than speculation or dramatization, liking this video and subscribing to the channel directly supports that approach. Everything on this channel follows the same evidence-first structure. If this interests you, there's a substantial archive already available, and turning on notifications ensures you see future content as it's released. To understand why these observations matter, we need to establish what distance actually means when observing the cosmos. The instinct is to think of space as a static stage where objects sit at fixed separations. That picture is fundamentally incorrect. Light propagates at 299,792 kilometers per second in vacuum. That speed is constant, measured repeatedly, and verified across every distance scale accessible to observation. But even at that velocity, separation immediately introduces delay. Light reflected from an object 1 meter away reaches your eye roughly 3 nanoseconds after leaving the surface. Across a room, the delay extends to tens of nanoseconds. From a building a kilometer distant, light arrives 3 microseconds late. These delays are measurable with precision instruments, though far too brief to affect human perception. The Moon orbits Earth at an average distance of 384,400 kilometers. Light from the lunar surface requires 1.28 seconds to traverse that gap. If the Moon were suddenly removed from existence, observers on Earth would continue seeing it for slightly more than 1 additional second. The Sun sits approximately 150 million kilometers away. Solar photons take 8 minutes and 20 seconds to complete that journey. Any event occurring on the solar surface, a flare, an eruption, a sudden extinguishment, would remain invisible to Earth-based observers for that duration. We do not observe the Sun as it exists now. We observe it as it existed 8 minutes and 20 seconds ago. Proxima Centauri, the nearest star beyond our solar system, lies 4.24 light-years distant. Every photon arriving from that star tonight departed in early 2021. The galactic center, located roughly 26,000 light-years away, appears to us as it existed 26,000 years in the past, predating agriculture, written language, and recorded civilization. The Andromeda Galaxy, visible to naked eyes under dark skies as a faint smudge, transmits light across 2.5 million light-years of intervening space. The photons entering your retina when you observe Andromeda left their source stars when early hominids were beginning to diverge from other primate lineages on Earth. Each of these statements is verifiable through parallax measurements, standard candle techniques, and spectroscopic redshift analysis. Distance and time are inseparable in observational astronomy. To look farther is, without exception, to look deeper into cosmic history. But the universe introduces an additional complication. Space itself is not static. It expands. This expansion was first measured in 1929 by Edwin Hubble, who observed that galaxies beyond our local group exhibited redshifts proportional to their distances. The farther the galaxy, the more its light was stretched toward longer wavelengths. Subsequent observations confirmed the pattern across increasingly large distance scales. The expansion is not galaxies moving through space like debris from an explosion. Space itself grows. The separation between gravitationally unbound objects increases because the space separating them continuously enlarges. A functional analogy: dots marked on a balloon's surface move apart as the balloon inflates, not because the dots slide across the rubber, but because the surface between them stretches. Similarly, galaxies recede from one another as space expands. This expansion stretches light traveling through it. A photon emitted with a particular wavelength traverses expanding space for billions of years. During that journey, space grows, and the photon's wavelength extends proportionally. Ultraviolet light shifts into the visible spectrum. Visible light shifts into infrared. Infrared shifts into longer wavelengths still. This effect, called cosmological redshift, is measured precisely using spectroscopy. Specific emission lines from hydrogen, oxygen, and other elements have known laboratory wavelengths. When those same lines appear in the spectrum of a distant galaxy, their wavelengths are longer. The ratio between observed and emitted wavelengths reveals how much the universe has expanded since the light departed. Redshift serves as a cosmic timestamp. High redshift values correspond to light emitted when the universe was young and much smaller. Low redshift values indicate more recent emission. Astronomers use the symbol Z to denote redshift. A galaxy at Z equals 1 emitted its light when the universe was roughly half its current age. A galaxy at Z equals 10 emitted light when the universe was only about 500 million years old. For decades, telescopes optimized for visible wavelengths, the portion of the spectrum human eyes evolved to detect, dominated observational astronomy. Hubble Space Telescope, launched in 1990, transformed our understanding of nearby galaxies, star-forming regions, and nebulae. Its visible and near-ultraviolet instruments captured extraordinary detail across objects within a few billion light-years. But as astronomers attempted to observe galaxies at higher redshifts, those existing in the universe's first billion years, a fundamental limitation emerged. Light from those early galaxies had been stretched by cosmic expansion into infrared wavelengths beyond Hubble's optimal range. The early universe wasn't invisible, but much of its light had shifted out of reach. James Webb Space Telescope was designed specifically to detect that shifted light. Its primary mirror spans 6.5 meters in diameter, composed of 18 hexagonal beryllium segments, each coated with a microscopically thin layer of gold. Gold was chosen because it reflects infrared wavelengths with exceptional efficiency, far better than the aluminum coatings used on visible light telescopes. Webb does not orbit Earth. It resides at the second Lagrange point, approximately 1.5 million kilometers away, where gravitational forces from Earth and Sun balance, allowing the telescope to maintain a stable position with minimal fuel expenditure. That location serves a critical function. To detect faint infrared signals from the early universe, Webb must remain extremely cold. Infrared radiation is closely associated with thermal emission. A warm telescope would glow brightly in the same wavelengths it attempts to observe, drowning out distant signals beneath its own heat signature. Webb addresses this with a 5-layer sun shield, each layer separated by vacuum gaps. The shield measures approximately 21 by 14 meters when fully deployed, roughly the size of a tennis court. Positioned between the telescope and the sun, it blocks direct sunlight and reflects heat away, allowing the shadowed instruments to cool passively. On the sunlit side of the shield, temperatures reach approximately 85 degrees Celsius. On the shadowed side, temperatures drop below -230 degrees Celsius. Some instruments are cooled further, reaching -266 degrees Celsius, only 7 degrees above absolute zero. At these temperatures, Webb's infrared detectors can register individual photons arriving from galaxies at redshifts exceeding Z equals 13. These are among the most distant objects ever observed, their light emitted within the universe's first 400 million years. Webb's observing process is patient. To capture extremely faint objects, the telescope often stares at the same patch of sky for many hours, accumulating photons gradually. Each exposure is carefully calibrated to remove noise, correct for instrumental artifacts, and subtract interference from cosmic rays striking the detectors. The result is not an instantaneous snapshot. It's an integrated record, thousands of photons collected over extended periods, each carrying information about conditions billions of years ago. When processed, these images reveal galaxies invisible to every previous telescope. One of Webb's early observations targeted a region called SMACS 0723, a massive galaxy cluster located roughly 4.6 billion light-years away. The cluster's gravity bends and magnifies light from even more distant galaxies positioned behind it, a phenomenon called gravitational lensing, predicted by general relativity and confirmed through decades of observation. Webb's deep image of SMACS 0723 captured thousands of galaxies, some at redshifts exceeding z=13. The faintest objects in the image required more than 12 hours of exposure time. Their light had been traveling for over 13 billion years, emitted when the universe was roughly 400 million years old. This is what astronomers mean when they say Webb looks backward through time. The telescope does not observe distant galaxies as they exist today. It observes ancient light, emitted long ago, preserved in transit across billions of light years. For much of the 20th century, theoretical models predicted a relatively quiet early universe. Following the Big Bang, space expanded and cooled. Matter spread outward almost uniformly, with only tiny density fluctuations imprinted during the universe's earliest moments. Gravity gradually amplified those fluctuations, pulling matter into clumps, but the process was expected to be slow. According to these models, the first stars formed several hundred million years after the Big Bang. Those stars gathered into small, primitive galaxies, faint systems containing only a few million solar masses. Larger galaxies would take hundreds of millions of years longer to assemble, growing through mergers and gradual accretion. This timeline was supported by indirect evidence. Observations of the cosmic microwave background, the faint radiation left over from roughly 380,000 years after the Big Bang, showed tiny temperature fluctuations corresponding to density variations. Computer simulations tracked how gravity would amplify those variations over billions of years, producing structure that matched the galaxy distribution observed in the nearby universe. Everything appeared consistent. Then Webb began observing. In July 2022, Webb's near-infrared camera captured spectroscopic data from galaxies at redshifts between z=10 and z=13. Initial photometric estimates suggested even higher redshifts, though later spectroscopic confirmation revised some downward. Regardless, the observations revealed galaxies existing 400 to 600 million years after the Big Bang. The surprise wasn't their existence. Theoretical models predicted some galaxies should form in that era. The surprise was their number and brightness. One study, published in Nature in February 2023, analyzed Webb's data and reported galaxy number densities roughly twice those predicted by standard models. Another study, published in the astrophysical journal Letters in November 2022, identified 6 massive galaxy candidates at redshifts between z=7.4 and z=9.1, each containing stellar masses between 10 billion and 100 billion solar masses. If confirmed, these objects would have assembled far more rapidly than conventional models allow. Further observations refined the numbers. Some initial mass estimates were revised downward after accounting for contributions from active galactic nuclei, supermassive black holes feeding on surrounding gas and emitting intense radiation. But even after corrections, the early universe contained significantly more massive galaxies than expected. Why does this matter? Galaxy formation is not instantaneous. It requires multiple sequential steps. First, dark matter must clump under gravity, forming massive halos. Then, ordinary matter, hydrogen and helium gas, must fall into those halos and cool sufficiently to collapse. Once dense enough, the gas ignites nuclear fusion, forming the first stars. Those stars burn through their fuel, synthesize heavier elements, and die, often in supernova explosions that enrich the surrounding gas. Subsequent generations of stars form from this enriched material. Each step imposes time constraints. Gas doesn't cool instantly. Gravity doesn't pull matter together instantaneously. Stars require millions of years to complete their life cycles. According to detailed simulations, assembling a galaxy containing tens of billions of solar masses should require at least 500 million to 1 billion years. Webb detected such galaxies when the universe was only 400 million years old. Some astronomers initially questioned whether the mass estimates were accurate. Perhaps the galaxies appeared brighter than they truly were due to intense star formation rates, or perhaps gravitational lensing was amplifying their light. Follow-up observations tested these possibilities. Spectroscopic analysis confirmed the distances. Detailed photometric measurements, comparing luminosity across multiple infrared wavelengths, allowed astronomers to estimate stellar masses independently of assumptions about star formation rates. The results consistently showed galaxies more massive than expected. In December 2022, a study published in the Astrophysical Journal reported spectroscopic confirmation of a galaxy at Z equals 13.2, existing roughly 325 million years after the Big Bang. Its estimated stellar mass exceeded 400 million solar masses. The authors noted that forming this much stellar mass in such a short time required star formation efficiencies significantly higher than those observed in the local universe. Star formation efficiency measures what fraction of available gas actually forms stars. In nearby galaxies, typical efficiencies range between 1% and 10%. Most gas remains unconverted, heated by radiation, disrupted by stellar winds, or expelled by supernova explosions. Early galaxies may have operated differently. The universe was denser. Gas clouds collided more frequently. Without heavy elements to complicate cooling, gas could collapse more efficiently. Mergers were common, compressing gas and triggering intense bursts of star formation. But even optimistic efficiency models struggle to explain the most massive early galaxies Webb has observed. Some researchers have proposed alternative explanations. Perhaps the initial mass function, the distribution of stellar masses, differed in the early universe, producing more massive stars that contributed more light per unit mass. Perhaps dark matter halos formed faster than simulations predict, accelerating structure assembly. None of these explanations has been definitively confirmed. The observations simply don't match standard predictions. This discrepancy is sometimes referred to as the impossibly early galaxy problem, though that phrasing overstates the situation. The galaxies exist. The observations are reliable. What's impossible is fitting them into previous theoretical frameworks without adjustment. Webb has also detected supermassive black holes at surprisingly high redshifts. In November 2023, astronomers using Webb identified a quasar, a luminous object powered by a feeding supermassive black hole, at redshift C equals 10.1. The black hole's mass, estimated from the quasar's brightness and spectral properties, exceeded 1 billion solar masses. This presents a separate puzzle. Black holes grow by accreting surrounding matter, but that accretion has physical limits. As matter spirals into a black hole, friction heats it to millions of degrees, causing it to emit intense radiation. That radiation exerts outward pressure, counteracting gravity and limiting how fast matter can fall in. This limit, called the Eddington limit, constrains black hole growth rates. Even under ideal conditions, constant inflow of gas, no disruptions, maximum accretion efficiency, a black hole can roughly double its mass every 50 million years. Starting from a stellar mass black hole formed by the collapse of a massive star, typically 10 to 100 solar masses, reaching 1 billion solar masses through continuous accretion would require at least 500 million to 700 million years, even at the Eddington limit. Webb detected this black hole when the universe was approximately 480 million years old. The timeline is tight. Either the black hole formed from an unusually massive seed, perhaps through direct collapse of a massive gas cloud, bypassing the stellar formation stage, or it grew faster than the Eddington limit allows through episodic super-Eddington accretion. Both scenarios are theoretically possible but require specific conditions. Direct collapse requires pristine gas clouds, free of heavy elements, with sufficient mass and low angular momentum. Super-Eddington accretion requires continuous gas supply and conditions that suppress radiation pressure. These observations do not overturn established physics, but they narrow the parameter space. The early universe must have supported conditions that allowed rapid black hole formation and growth, even if we don't yet fully understand the mechanisms. For decades, astronomers estimated the observable universe contained several hundred billion galaxies. That number came primarily from Hubble's deep field observations, images capturing tiny patches of sky and counting every visible galaxy. Hubble's most famous deep field, the Hubble Ultra Deep Field, covered an area roughly 1/10 the apparent diameter of the full moon. Captured over 4 months in 2003 and 2004, The image required 11.3 days of total exposure time, accumulating light from nearly 10,000 galaxies. Scaling that count to the full sky yielded an estimate of approximately 200 billion galaxies in the observable universe. Later refinements, accounting for galaxies too faint for Hubble to detect, raised the estimate to several hundred billion. Then Webb observed the same regions. Where Hubble detected galaxies as faint smudges separated by black gaps, Webb revealed continuous structure. The black gaps were not empty. They contained galaxies whose light had redshifted beyond Hubble's detection range. In one deep field observation, Webb captured an area roughly 3 times the size of the full moon. Over several hundred hours of exposure time, the telescope recorded nearly 800,000 individual galaxies. 800,000 galaxies in a region covering approximately 0.01% of the total sky. If that density is representative, and observations in other directions suggest it is, the total number of galaxies in the observable universe may exceed 2 trillion. This is not speculation. It's extrapolation from measured galaxy counts across multiple independent fields. The number could be refined as more data accumulates, but the order of magnitude is established. Why did Hubble miss so many? Redshift. As galaxies recede, their light stretches into longer wavelengths. Hubble's instruments were optimized for visible and near-infrared wavelengths, with sensitivity peaking around 0.8 to 1.6 micrometers. Webb's instruments extend from 0.6 micrometers to 28 micrometers, covering mid-infrared wavelengths where highly redshifted galaxies emit most of their light. Additionally, many galaxies are heavily obscured by dust. Dust absorbs visible light but allows infrared wavelengths to pass through. Hubble saw darkness where Webb detected glowing, star-forming galaxies hidden behind dust clouds. These galaxies are not dim. Many are forming stars at rates exceeding 100 solar masses per year, far faster than the Milky Way's current rate of roughly 1 to 2 solar masses per year. Their infrared luminosity rivals the brightest galaxies in the nearby universe. They were always there. Previous telescopes simply couldn't see them. Webb's deep fields also reveal large-scale structure with unprecedented clarity. Galaxies are not randomly distributed. They cluster along filaments, forming a cosmic web that stretches across hundreds of millions of light-years. This structure arises from gravity amplifying tiny initial density fluctuations. Regions slightly denser than average exerted slightly stronger gravitational pull, attracting nearby matter. Over time, matter flowed into these overdense regions, forming filaments and leaving vast underdense voids behind. Computer simulations predicted this structure, but Webb has now mapped it directly across cosmic time. One study, published in the Astrophysical Journal in August 2023, used Webb data to construct a three-dimensional map of galaxy distributions spanning redshifts from z equals 0.5 to z equals 7. The map reveals filaments already well established when the universe was less than 1 billion years old. One particularly striking structure, observed at redshift z equals 3.44, consists of more than 20 massive galaxies aligned along a filament extending 13 million light-years. Several of these galaxies have already stopped forming stars. They've exhausted or lost their gas reservoirs despite the universe being only 2 billion years old. This indicates that galaxy evolution is accelerated in dense environments, where interactions and mergers rapidly consume gas. The cosmic web is not merely decorative. It channels matter. Gas flows along filaments like water through rivers, feeding galaxies at intersection points. Galaxies don't evolve in isolation, they're connected, supplied by streams of inflowing material that sustain star formation over billions of years. Webb has also cataloged the largest sample of galaxy groups and protoclusters ever assembled at high redshift, more than 1,600 systems spanning redshifts from z equals 0.5 to z equals 4. These groups represent the building blocks of today's massive galaxy clusters. By comparing groups at different epochs, astronomers can directly observe how structure evolves. Early groups appear irregular and chaotic. Star formation rates are high. Later groups show increasing order, smoother morphologies, and declining star formation as they mature into relaxed clusters. Between the filaments lie cosmic voids, regions spanning tens to hundreds of millions of light-years containing very few galaxies. These voids are the largest structures in the universe by volume. They're not completely empty, but their galaxy density is far below average. Voids form because gravity pulled matter out of these regions and into surrounding filaments and clusters. They represent the complement to structure, places where structure formation failed. Webb's images capture this contrast starkly. Dense clusters packed with thousands of galaxies sit adjacent to vast black regions containing almost nothing. The universe is both crowded and empty, depending on where you look. When people first learned that the Big Bang occurred approximately 13.8 billion years ago, the natural assumption is that the most distant observable objects should lie roughly 13.8 billion light-years away. Light has had 13.8 billion years to travel, so it should have covered 13.8 billion light-years of distance. That reasoning is incorrect. The observable universe has a radius of approximately 46.5 billion light-years, giving it a diameter of roughly 93 billion light-years. This is not theoretical speculation. It's calculated directly from measured expansion rates and confirmed through observations of the cosmic microwave background. The discrepancy arises because space itself expands. When a distant galaxy emitted the light we observe today, it was much closer to us. While that light traveled toward Earth, the space between us and the galaxy continuously stretched, carrying the galaxy farther away. By the time the light arrived, the galaxy had receded to a far greater distance than the light's travel time would suggest. A precise example: the most distant galaxy confirmed by Webb, Jade's GSC 14-0, sits at a redshift of z equals 14.32. Its light has been traveling for approximately 13.5 billion years. But the galaxy itself is currently located roughly 33.8 billion light-years away, because space expanded significantly during the light's journey. This is not faster than light motion. The galaxy isn't traveling through space at impossible speeds. Space itself is growing, carrying the galaxy along. General relativity permits space to expand at any rate. There's no speed limit on spatial expansion itself, only on objects moving through space. This expansion creates a boundary called the cosmic horizon. Beyond approximately 46.5 billion light-years, space is receding so rapidly that light from those regions will never reach us, no matter how long we wait. This horizon is not an edge of space. It's an edge of observability. Space continues beyond it. Galaxies continue forming, evolving, and dying in regions that are permanently inaccessible to our observations. The cosmic horizon is not static. It grows slowly as the universe ages, because light from slightly more distant regions has additional time to reach us. However, cosmic expansion is accelerating, driven by dark energy. This acceleration counteracts the horizon's growth, and in the far future, expansion will dominate completely. Current measurements indicate that the universe's expansion rate, quantified by the Hubble constant, is increasing. This acceleration, first detected in 1998 through observations of distant Type I supernovae, implies that galaxies beyond our local group are receding faster over time. If this continues, galaxies currently visible will eventually cross the cosmic horizon and disappear from view. Their light will redshift into undetectable wavelengths, and no new photons will arrive. In roughly 100 billion years, assuming expansion continues accelerating, every galaxy outside the local group, our gravitationally bound collection of nearby galaxies, will have receded beyond the horizon. Future observers would see a universe containing only their local cluster, surrounded by darkness. They might never know anything else existed. This is not distant speculation. It follows directly from measured expansion rates and well-tested cosmological models. The observable universe is not the universe. It's the portion we can access from our location in space and time. Move to another galaxy, and the observable universe changes. Different regions enter view while others disappear. Two galaxies can both be visible from Earth yet unable to observe each other. They may sit on opposite sides of our cosmic horizon. Light from both reaches us, but light from one can never reach the other. There's no privileged vantage point. Every observer sits at the center of their own observable bubble, surrounded by regions they can never access. The discovery that cosmic expansion is accelerating was entirely unexpected. For most of the 20th century, cosmologists debated whether expansion would continue forever or eventually reverse. Both scenarios assumed gravity was slowing expansion down. In the late 1990s, two independent research teams, the Supernova Cosmology Project and the HISE Supernova Search Team, measured distances to Type I supernovae in distant galaxies. Type I supernovae are useful because they have consistent intrinsic brightness, making them reliable standard candles for measuring distances. The teams compared observed brightness to known luminosity, determining distances to dozens of supernovae at redshifts between z equals 0.3 and z equals 1. They then compared those distances to the galaxy's recession velocities, measured from redshift. The results were incompatible with a decelerating universe. Distant galaxies were farther away than they should be if expansion were slowing. The only explanation, expansion had been speeding up for billions of years. This discovery earned the 2011 Nobel Prize in Physics. It also forced cosmologists to introduce a new component, dark energy. Dark energy does not emit, absorb, or scatter light. It does not clump into galaxies or interact with ordinary matter. We infer its existence solely from its effect on cosmic expansion. Current measurements indicate dark energy comprises approximately 68% of the universe's total energy density. Ordinary matter, everything made of atoms, accounts for less than 5%. Dark matter constitutes most of the remaining 27%. What makes dark energy especially strange is how it behaves as space expands. Ordinary matter dilutes, double the volume, and density drops by half. Radiation dilutes even faster. Dark energy's density remains constant. As space grows, the total amount of dark energy increases proportionally. More space means more dark energy, which accelerates expansion, creating even more space. This feedback loop shifted the balance of cosmic power. Early on, matter dominated, allowing gravity to assemble galaxies and clusters. But as expansion diluted matter, dark energy's influence grew. Approximately 5 billion years ago, dark energy became the dominant driver of cosmic expansion. Webb doesn't detect dark energy directly, but its influence permeates every observation. The extreme redshifts Webb measures, the vast size of the observable universe, the way distant galaxies fade, all reflect dark energy's accelerating effect. Without dark energy, the observable universe would be significantly smaller. Regions Webb now observes would lie beyond the cosmic horizon, forever inaccessible. Yet dark energy introduces a profound mystery called the Hubble tension. When astronomers measure the current expansion rate using different methods, they get inconsistent results. One method examines the cosmic microwave background, radiation released 380,000 years after the Big Bang. Detailed measurements by the Planck satellite revealed temperature fluctuations across the sky. From these fluctuations, physicists calculate the expansion rate should be approximately 67 km per second per megaparsec. Another method uses direct distance measurements to nearby galaxies, calibrated with Cepheid variable stars and Type I supernovae. This approach consistently yields approximately 73 km per second per megaparsec. Both measurements are precise. Both have been repeated. They disagree by roughly 9%, a discrepancy far larger than measurement uncertainties. Webb was expected to resolve this tension by refining distance measurements. Instead, Webb's observations confirmed the higher expansion rate. The disagreement persists. This leaves three possibilities: unknown measurement errors, incomplete understanding of the universe's composition or history, or new physics beyond current models. Each possibility carries significant implications. The expansion rate determines the universe's age, size, and ultimate fate. Misunderstanding it means many cosmological conclusions require revision. One possibility is that dark energy's strength changes over time. Current models assume it remains constant, but if it strengthens or weakens, expansion history would differ from predictions. Another possibility involves the early universe. Tiny deviations in initial conditions could propagate forward, affecting expansion rates in ways current models don't capture. More extreme scenarios exist. If dark energy strengthens over time, expansion could eventually overcome gravity even on smaller scales. Galaxy clusters would dissolve. Galaxies would be torn apart. In the most extreme case, called the Big Rip, even atomic nuclei could be disrupted. Current evidence does not favor this outcome, but uncertainty remains. What's clear is that dark energy dominates the cosmos. It stretches space, determines what we can observe, and shapes the universe's long-term evolution. Yet it cannot explain the universe we see alone. While dark energy pulls space apart, something else must pull matter together. Without it, galaxies could never form. Structure would dissolve into uniform emptiness. That force is equally invisible, equally mysterious, and far more massive than everything we can see. If dark energy governs cosmic expansion, dark matter governs structure formation. Without dark matter, galaxies wouldn't exist. Clusters wouldn't form. The cosmic web wouldn't emerge. Dark matter doesn't emit light. It doesn't absorb radiation. It doesn't interact electromagnetically. Yet it outweighs visible matter by more than 5 to 1. Approximately 85% of all matter in the universe is dark matter. Every galaxy, every star, every glowing nebula exists within a framework dominated by invisible mass. What we observe is merely the illuminated surface of a deeper architecture. Evidence for dark matter emerged nearly a century ago. In the 1930s, astronomer Fritz Zwicky measured velocities of galaxies within the Coma cluster. The galaxies moved far too quickly to be held together by visible matter alone. He proposed the cluster contained large amounts of unseen mass, dark matter. In the 1970s, astronomer Vera Rubin studied rotation curves of spiral galaxies. Stars in galactic outskirts orbited at speeds that should have flung them into intergalactic space if only visible matter existed. They remained bound, moving as if embedded in massive, invisible halos. Subsequent observations across multiple wavelengths and techniques confirmed the pattern. Gravitational lensing, the bending of light by mass, predicted by general relativity, revealed mass distributions far exceeding visible matter. Galaxy clusters showed similar discrepancies. Everywhere astronomers looked, gravity indicated more mass than light revealed. Dark matter's importance extends beyond its abundance. Its behavior fundamentally differs from ordinary matter. Dark matter doesn't collide with itself or emit radiation, allowing it to move through space almost without friction. Because of this, dark matter began clumping extraordinarily early. Shortly after the Big Bang, tiny density fluctuations existed in matter distribution. Dark matter responded immediately, gravitationally attracting nearby dark matter and forming growing concentrations. Ordinary matter remained hot and resistant to collapse for hundreds of thousands of years. Dark matter halos grew undisturbed during this period, creating deep gravitational wells. When ordinary matter finally cooled enough to collapse, it fell directly into these pre-existing dark matter halos. Gas collected, compressed, heated, and ignited nuclear fusion. Stars formed. Galaxies assembled, not randomly, but precisely where dark matter had already laid foundations. The visible universe traces an invisible blueprint. This process produced the cosmic web. On the largest scales, matter arranged into filaments stretching hundreds of millions of light years, intersecting at dense nodes and separated by vast voids. Webb's observations have mapped this structure across cosmic time. Galaxy catalogs constructed from Webb data reveal filaments already well established when the universe was less than 1 billion years old. Matter flows along these filaments physically. Gas streams through space like traffic along highways, feeding galaxies at intersections. Galaxies don't evolve in isolation. They're connected through channels defined by dark matter's gravitational pull. Recently, astronomers detected dark matter directly along filaments using gravitational lensing. By measuring subtle distortions in background galaxy images, they revealed mass where no visible matter exists. Dark matter isn't confined to galaxy halos, it threads the entire universe together. At the densest nodes lie galaxy clusters, the most massive gravitationally bound structures in existence. These clusters act as anchors, pulling matter inward and transforming infalling galaxies. Gas is stripped away. Star formation halts. Structures deform. Webb has captured galaxies mid-transformation, revealing how environment shapes evolution. Despite dark matter's influence, its nature remains unknown. We don't know what it's made of. Leading candidates include weakly interacting massive particles, WIMPs, axions, or primordial black holes formed in the early universe. Decades of laboratory experiments have searched for dark matter particles. None have been detected. Yet its gravitational effects are undeniable. Remove dark matter from cosmological models, and structure formation fails. Galaxies don't assemble. The cosmic web doesn't emerge. The universe remains nearly uniform. Webb reinforces dark matter's central role by revealing how quickly structure formed. Visible matter alone couldn't have done it. Dark matter provided the essential head start, allowing gravity to build complexity before ordinary matter even began collapsing. The universe exists in tension between two invisible forces. Dark matter builds structure. Dark energy stretches space. On small scales, gravity dominates, allowing galaxies and clusters to form. On large scales, expansion prevails, pushing regions beyond every horizon. Webb has shown the universe is more organized, interconnected, and dependent on unseen forces than previously imagined. What we see, stars, galaxies, glowing clouds, is only the illuminated surface. Beneath lies invisible architecture. Beyond lies inaccessible vastness. And both are fundamentally real, supported by measurement, observation, and verified physical law. If you appreciate content built entirely on experimental evidence, peer-reviewed research, and measured data rather than speculation, subscribing and liking the video ensures more of this reaches the right audience. The entire channel follows this evidence-first approach. You'll find many similar videos already available, and turning on notifications means you'll see future content as it's released.